Hello again, my RF and microwave circuits design engineers. Welcome back. I'm Dr. Mohamed Nezami. I'm an RF and microwave circuits design contractor operating from Jerash City, Jordan. We are continuing the series that I started on the RF radio frequency and microwave circuits post layout verification and validation process. We have done so far 3 sessions, and this is the 4th session of the 4 sessions that are based on Pathwave, ADS, and RF Pro and System View from Keysight. So you can refer back to these videos in here. Today I'm just going to continue one more part. I may have one more also, and that's it. And then we will turn our effort to doing the same thing, except in the HFSS HFSS ANSYS system. Now you recall that we had a board that was a KU band LMB board that is here, where for a client that I designed, and PCB layout I did, and we looked at the we took this board and we wanted to do some kind of post layout verification, because some of these modules were designed in synthesis programs like ADS and like Genesis and System View. So we wanted to make sure that the performance did not get corrupted along the way while we transferred the image of microstrip work from these packages using either transformation via DXF or some other way of doing it, that we took this into a cadence library, and then we use the cadence library symbols of footprints as footprints. We use these systems and we brought them in, and we want to make sure that when we by the time we added all the stack layer things around it, all the copper core, all the vias, that nothing had went wrong. Okay. So today, last time we did the filters, we did the radial stops on the LNA portion. Today, I'm going to go further into the IF stage, okay? Now, you may recall that this is the system that I'm doing, and this system, I did it back in a video that you might want to refer back to this video here. This was about a year ago that I did this. So you can take a look at this again and view all the things that we did here, okay? So today, let's go further into this section here, which is the IF section filter, which is from 950 to 1700, or from 1000 to 2000 gigahertz. That's what I like to call it. There are 2 filters in here. They're ceramic filters, and we want to take a look at the performance of those. Now, these ceramic filters, let me just show you these components. So this is the IF section, and we want to take a look at the IF stages. There's two amplification stages and 2 filtering stages. And these filters are high Q ceramic filters that we would like to take a look at. This is from the previous sessions. So again, schematic wise, this is really what I have. I have 2 filters, ceramic filters, and some passive components around it. And I'll talk in a minute what these are. This filter is provided by Mini Circuits, and you can take a look at the data sheet in here. It's basically from 950 to 1970 with this part number. Now, this part is really a 75 ohm part, and our system is a 50 ohm system. So what I have right now is these two. These are the 2. This is the filters right here. So let me point just for simples. So this is one filter, and this is another filter, okay? So we come in here from a previous amplification stage, and then we go into the first filter, and then we have the second one in here, and then we have some kind of microstrip line that feeds the following amplification session. And like I showed you last time, what we did to this board is we exported this board in ODB++, and we imported it into the ADS. Okay, we imported this board like this. This is basically the board imported in as an ODB++, and the reason we do that is because we need to make sure that we retain the third dimension where we can get the stack layer, the full stack layer in there. Right now, this is, even though it's a 10-layer board, I just brought in the top layer, which is the microstrip work, and the ground plane that is right beneath it. So that's all I need. And of course, the material is Rogers material, 20 mils. So what we're going to do is we're going to come into the IF section that is here, okay? And we're going to chop this part here and analyze it, okay? So we're going to go like this. We could do it, let's go this way. And so we're going to go to here. Okay, I'm just going to use arbitrarily any of the layers to create a zone. And we're going to go to tools, cookie cutting, and we're going to cut that out. So right now, I've only got this portion here, and this is basically the portion that contains the IF stages. Okay, so we've got, these are the two filters, one in here, one in here. There's the belly pad, ground pad, and there's the input and output. That's one filter, and this is another filter. So these two filters are 75 ohm systems. And this board, of course, if you were to look at it in third dimension, it's I'm bringing in the ground, which is here, and this is the vias that connect the top and bottom copper. Okay, so what we want to do is we want to verify the RF performance from this point onward to this point here. Okay, and that's so the way we do that is that first we can go in here and just basically put pins on there. So we're going to go to the top layer, and we're going to go put pins in the corresponding ports that we need to look at. The one right here, we'll put one here, one here. We put all the ports, we put pins on them. Okay, so we're ready now. This is ready. And then what we're going to do, we're going to set up EM simulation process where we can basically look at the frequency response of the portions that we have. But what we're going to do is the most important thing is that we want to, the way to simulate this, when we simulate it, we get an EM model, but it only gives you the response from this point to this point. We need to insert the filter in here. So what we're going to do is we're going to go to this part here and create basically a component and create an EM model of this. Create a symbol, and that symbol we're going to actually look at it. And when we sweep it, we're going to go and interconnect, bring it into schematics, and interconnect the filters and so forth between this point and this point and this point and that point, and then sweep the whole thing. So let me just take you to, I did that already. So yeah, let's just take a look at that. So this is the layout that I did already, and let me take out the meshes. Let's clear out the, okay, so this is what I got, is this is the piece of board that we have. What I want to do is from this point to this point, I want to sweep this. And I already created an EM model for this. So and let's just show you what this component is basically. So we've got this section where the IF filters are sitting right here. Now this filter, of course, let's look at this filter closely. Why is it this way? So we got a little tiny piece right here, like a peanut size ceramic chip. And you can go to the data sheet on this filter. And when you go to the data sheet, Minisex gives you, of course, like any other manufacturer, they give you a data sheet. They give you the S parameters, which we're going to use. We're going to download this. And also, we're gonna, one thing important, we're gonna look at the PCB layout recommended by them. And we're just gonna follow exactly the way they do it, okay? And so let's look at the data sheet, for instance, on this. It's just, hopefully this will download quicker. So we get back here. So now once I run this, of course, okay, here's the data sheet, and the data sheet in there, you can see all the parameters, all the frequency response, and it gives you here is the PCB layout for this part. So what we want to do is we want to create an input pin, an output pin, and a belly on the bottom with two vias in there, just like they did here, okay? So this is the PCB LAN pattern that we're going to utilize. And then, of course, around it, you're going to put a fence of wall of vias, just so that we get more and more isolation on this, okay? So, but more important, we're going to get the S parameter, and I'll tell you why we're going to get the S parameters from them. So this board here, after I ran it, I created this model, which has, this is lookalike, they call it layout lookalike symbol. What it is, it's basically an EM model of this piece with these inputs that are here, okay? And this model, I'm going to take it and place component, and we're going to go to the schematics, of course, and I'm going to put it in here, like I did in here, and I'm going to bring in a two-port network, generic network, with that will point to a file that is this file in here. And this file in here, as you can see, this file here, it's an S2P file that is from that I downloaded from mini circuits. That's this file here, and that's basically this parameter file of this. So I'm going to run this. So this is, and of course, the other thing I'm going to do is make sure that this is 75 ohm. Now, why I'm using a 75 ohm in a 50 ohm system? Well, first of all, this part was really made for the cable TV and for SATCOM receivers and modems, okay? Because a lot of them are 75 ohms. But this filter is really such a good part that I'm going to do is actually use it. Some people, what they might say is use 75 and 50 at these frequencies, they mismatch. It's okay, you still get a good response. But what I'm going to do, and if you look at the schematics that I showed, oh, no, I don't want it here, that I showed earlier, in the schematics, I'm going to basically use an LC section on both sides of the filter so that I can match it to a 50 ohm. So this is a mimic amplifier in here and a mimic amplifier in here. These are 50 ohm systems. So I'm going to use, and in the next session, I'm going to use co-simulation again, where I use the same symbol to do the basically the matching in here, just to make sure that find the optimal value for this capacitor and this inductor. So right now I run this, okay, I run, the other thing I want to do is let's look for the sake of just experimentation, is we're going to look at just the device alone, what the S parameter look like, the transmission and reflection. And then we're going to look at the also a cascade of two of them, okay? What I have here is two of these devices, and I'm going to basically look at these two of them, okay? Let's see this out of the way, okay? So we're going to do a comparison between this here, basically two cascaded of these ceramic filters being used in a co-simulation with the S parameters and the EM model of the copper from the layout that I have here, the actual layout that I exported. So we're going to run this, and I did already run it, okay? And this is the, here's, okay, I guess I didn't keep it, so let's do it again. So let's, okay, if we look at the schematics, this is port 1 and 2. So let's take a look at this one, or let's start with just a single device, how it looks like. So we got 5 and 6, port 5 to 6. So I'm going to ignore this. I'm going to come in here and get this, and hopefully it skipped the data. I have it. So we're going to look from 5 to 6, and let's look at one of the return loss ports in there. Okay, so I'm going to go again, and here's the, like I said, this is the single device, ideally how it looks like. So we're going to run the simulations, and we're going to simulate again. Okay, so it ran, and now I'm going to get basically 5 to 6 is the port that I have. So we're going to go 5 to 6. I'm going to look at the return loss, port number 6, and that's what we get here, okay? And let's put some markers on this. So, I'm going to put a marker right here. Let's make this at a gigahertz. Okay, and let's put another marker at 2 gig. Okay, it's this one here, so we're good. The worst case return loss is this value here, which is minus 12 dB, 12.7 dB. Okay, so you got the nice filter in here. So this is just, I'm going to thicken this line just so that we could distinguish it from the other ones, okay? And this one as well. Thicken it just a little bit. All right, so now let's go back, and what we want to do, and of course, to verify this, what we could do is we could go to the data sheet on this part, and let's see if I kept that. The data sheet on this part is this one here, and you could look at the response in here and actually verify if this is correct, and which is, it's pretty much the same. So okay, so what we're going to do, let's go further now. What we have, let's look at when we cascade 2 of them together, and that's port 3 to 4. So let me put that in here separate first. 3 to 4. Or 4 to 3, either one. It's a passive reciprocal network. So this is what we have. So this is the cascade of 2 of them. Okay, and if you can put, let's put markers again at around gigahertz and around 2 gigahertz to see the best band losses and the worst case return loss, which is this point here. And now we can see as a comparison, okay, when we cascade 2 75 ohm systems together, of course, the insertion loss is twice doubled, which is correct on both sides. And the return loss has deteriorated by around this much. It went down from minus 13 dB to about minus 8, okay? All right, so which is, that's the price that you get when you force cascading these together. So really what you, ideally, what that says, if that, what we need to do is we need to put an inner stage matching between them, even though they're two same systems, because the return loss is not so great on a single one of them. Now, let's go up here and see what it is for this part. When we include all the copper, all the vias, the ground effects, and all on the substrate. So let's go again, and we're going to go here, and those that one is, of course, is 1 to 2, right? This is 1, port 1, and port 2. Okay, so let's look at that. We're going to look at the port 1 return loss in here, and the insertion loss or the transmission, and here it is. So let's look again at the markers. So we can see that the let's put this at 2 gigahertz. So again, the insertion loss is very much the same, which we expect because the substrate is a good substrate. It's very low loss substrate, Rogers 4003, and the copper work is not a whole lot of copper distances that we are involved with. So okay, and then but the return loss, let's see the return loss worst case, it's about minus 8.8. Okay, so it's almost the same as if you put the two things together. It got a little improved, of course, because of the copper 50 ohm line interstaging between them, or 75 ohm. So that's what we get. Okay, so but now to many this is acceptable. Okay, especially when you're talking that this system in here, these two stages of filtering, these are really sitting among a cascade of many stages yet to go, because you've got two amplification stages, and you've got so let's again superimpose the the actual cascade, okay, of the co-simulated part. And you can see right here what happened is that the thick one is if you have what the manufacturer de-embedded port-to-port filter response, okay, and of a single one, okay, and that's why you get a little more loss, lower loss in here. Okay, but we want to look at the return loss. What concerns us is that this is the deterioration due to copper and the inner stage copper that involves in there. Okay, so basically now what we really have to do is that, we could go back to this circuit in here, and we say we really need to have an inner stage matching between these two to improve, or if you have enough gain in the addition, if you can afford a little extra gain, you throw in a 3 dB bipad resistors in here, 3 resistors, and that will improve a lot the isolation and reduce the interaction between these two that deteriorates the. So again, what we did is we used co-simulations and advanced design system from Keysight to bring in a chopped piece of the of my board that was done in Cadence in here. We brought in this piece in here, this portion in here. Okay, we cut this portion and we brought it in, and we ran the EM model on it. We meshed it and we did EM simulations on it by doing all these ports in place of where the passives are and where the two filters are. Of course, the filters, we followed exactly the same layout. As you can see here, the belly pad has two vias to the ground, and the rest is a lot of fencing of vias. Okay, and so what we did, we looked at the response of this, how it looks like compared to if ideally you only had no copper, if you just had two ceramic filters connected back to back, and then comparison to a single one, and that's what we got. Basically, we have deteriorated. This is the three of them. Let me take this back out, delete this, delete that. So we went from this one here, which is the ideal. This is the clean filter without any additional things attached to it. We went, when we cascade this, we went to this one in here, basically, where we have deteriorated in return loss, but still good enough, I would say, to be honest with you. So this is really good right now. You can even go without matching this, because the worst case return loss is minus 9 dB, and that's sufficient in this type of frequency and this type of PCB kind of work. So again, so what we're going to do next is let's go next week, hopefully one more session, and then we're going to repeat the same work, some selected work that we did earlier, like for instance, when we looked at these microstrip filters that are used in the layout in the board, these ones here. So what we could do is we could look at again, take this like we did in here as an ODB file into HFSS, and that's more powerful because we can do more 3D stuff. So we're gonna do the same thing and just show how we do that in there as well. Okay. Until then, I'd like to thank you again for following with me. Again, this is Dr. Mohamed Nezami. If you have any out of design work that you need to do and you need to offload some of your in-house, or you can't afford an RF designer in-house, I'm ready to work for you. My rate is very inexpensive. You can outsource the designs to me, and I will work with you from concept all the way to fab files. And we'll even come in-house at the during the prototyping and testing and help verify the prototype. You can reach me at this phone number in here. I can be reached also via the Androids and Apple iPhone these phone apps, WhatsApp and Telegram. Okay. Until then, I would like to thank you again. Thank you very much, and hopefully you enjoyed this. We'll see you in the next session. Thank you very much. Have a great day.